Hello, my name is Damian Berry. I am an applicant to be a part-time online teacher. I am currently a full-time teacher. I am a head of a physics department. I'm certified to teach all subjects. My specialty includes chemistry and physics, and I can teach those subjects at all levels. Today, I'm just going to have a basic lesson in a general physics class. I'm hoping that you can generally get a sense of my teaching style, a little bit of my personality, and how a class would go with me. So, without further ado, today we're going to be talking about a lesson in work, energy, and power. It's basically going to be an introduction to work, and we're going to talk about power at the end. The lesson objectives, we're going to look at the definitions and the mathematics of work. We're going to calculate the amount of work done by forces, and we will finish off today with a topic about power. Now, before we get started about work, I have a simulation, and I have a question for you. Say that part of your chores is that your parents are making you move the refrigerator across the apartment. Maybe you're moving, who knows. But let's think about it. To move that refrigerator requires work. We understand that in everyday life. Can we go ahead and bridge our knowledge of physics so that we can understand conceptually what it is to do work? So let's say that you're the stick figure and you want to move the fridge. What are you going to do? Yes, we would push it, which is applying a force, right? So let's say the person comes up, and let's say that you're pushing that fridge and you're putting a lot of effort into it, and you've got some force and it's not moving. My question is, have you done any work? Well, if your parents come into the kitchen and they see that the refrigerator is in the same place, they're not going to think you have done anything. Why? Because you've done no work. So what we understand is that for us to do that work, not only do we have to apply a force, I think there's way too much friction. We'll get rid of the friction. We apply a force, and it has to go a certain distance. We'll increase the friction to stop it. So, using this basic idea, can we come up with a formula for work based off of things that we know about from everyday life? Let's go ahead and do this. So, what we can say is that work, is equal to, not equal is not really nice looking, is it? And a force, in this case it was an applied force. Now, we know there's a distance, however, that's not quite right. If you remember back from kinematics, we're not going to say distance because if you push the refrigerator 3 meters to the right and then 3 meters to the left and your parents come in, it's in exactly the same place, you've done no work. Yes, you put effort to move it around, but the total work is zero. So what we're going to say is that work is equal to force times displacement. Now, as always, I'm going to cover the units for you. So work is equal to joules. It's named after the famous scientist James Joule. We will talk about him further in thermodynamics in a later unit. Of course, we know that force, we should be so familiar with this unit already. It's Newton. And then we're going to say delta x displacement is equal to meters. This is going to be our units. So what I have today, I have a sheet with some work that we're going to be working on today. First one, a student is trying to move a bookshelf. The student exerts themselves greatly, applying 55 newtons of force on the bookshelf, but it doesn't move. How much work does the student do? Oh, very smart. Let's go ahead and do this. We know that work is equal to force times displacement. The force is 55, the displacement is 0. 5 times 0 is 0. We've done no work. The second question, if 10 newtons of force is required to pull an object 5 meters, how much work is done? Work is equal to force times displacement. Force is 10 newtons, and the displacement is 5. It's going to give us 50 joules. Very basic. However, the equation that we have, it's a little incomplete. And the reason that I say that is because in general, a mathematical equation should be able to explain every situation. And I don't think this one does. Let me just go ahead and just erase this. And we're gonna investigate why I say that. Consider we were to have a box. And I'm going to get an orange one because I think that's really interesting. And let's say that we applied a force this. Let's say that we applied a, what is this? We apply the force in this direction. Which direction would we assume the displacement? Well, why does that matter? Well, let's consider something real quick. In our equation, we left something small out. And that something that we left out is the fact that force is a vector. And what do we know about vectors? Can I have somebody tell me? Student B. That's correct. Direction matters. Well, what does that mean? Well, in this situation, we pulled the box to the right. Let's do this. And what do we assume about the displacement? Well, we would assume that the displacement is in the same direction. So if we apply the force, we would assume that the displacement is in that same direction. But that isn't always the case. Sometimes we can apply the force in different directions. Consider a wagon. We don't pull the handle in the same direction that it's moving. We pull the handle upwards a little bit. And so what happens is that the force in that x component is going to be less because that is the resultant. When we're pulling this way, this is our resultant. The components are going to be different, and so we only care about the component in the direction that it's moving. So what does that mean? That means that we need to consider the direction of that force relative to the displacement. For this class, we're going to have it in just the one direction, which is to the right. So when we're considering this, if we were to have, and I'm just going to do a hypothetical, if we were to have a force in this direction, we would need to break this down into components in order to know the amount of force that is in the same direction as the displacement. Well, how do we do that? Well, if we remember back from vectors, we need to know the angle. Now, to consider this, if we take a look at our green and our blue, what we know is that the force is completely in the direction of the displacement. So what we need to do for the angle is we need to show that whenever the angle is 0, the work is going to be at a maximum. How did we do that? In vectors. What you should remember is that we use trigonometric identities to explain that. So we had the force times the displacement. If we were to include a term, cosine of theta, that would account for the direction. If you take a look at this, the force is in the same plane as delta x. Theta will be equal to 0. Cosine of theta is 1. When we look at that, what happens is that we are left with that original equation we were working with. Just by including that original term, this term, and showing that it's in the same direction, the cosine theta will cancel out, leaving our original equation. And that's kind of a powerful thing because it allows us to consider the direction of the force, which the equation really demands. So if we were to go back to our problem, we would have a problem here. It says that the box is moved according to the diagram below. They're applying 10 newtons of force, 30 degrees, and the box looks like it moves 50 meters. It asks the question how much work is being done. So work is equal to the force is 10 times delta x, it's going to be 50, times cosine of theta, which is going to be cosine of 30. Whenever I pull open the calculator for that, it's about 433. So work is equal to 433 kilojoules. If you take a look at this, the significant figures, this is 10, this is 50. Each of them has a significant figure of 1. So if you were to do 400 joules, that would be correct according to the significant figures. Although in my classes, I care more about you showing the work and you having an answer that reflects that work. So if you were to have either, if you showed your work, I would be okay with that. Okay? Let's take a look at the next problem. So, let me just go ahead and click enter a couple times so that we can see this. A student does an experiment using a sensor to measure the force of pulling a box across the table. The student graphed out the force against the distance on a computer. The question is, what is the work from B to C? What is the work from A to B? What is the total work from A to D? So let's go ahead. We're going to copy this and there we go. Move this guy over. So the challenge of this is being able to read a graph and to understand the information that's in the graph. we're asking about the force. What you should recognize is that force is equal, or I'm sorry, the work. The work is the force times the distance. Well, the first one that they're asking us for each points. And the first one that they asked us is from B to C. So from here to here. Now the thing is that we're kind of lucky because the force is a constant during that part. And you'll see why that's going to be helpful for us. So to know the amount of force during this time, it's just, whoops, it's going to be the height. And to know the distance, we would just record the x component of it. Pretty simple. We know that work is force times distance. This is the force, this is the distance. If we were to multiply those, basically what would happen is that we would start getting an area for this box. Now that's kind of important because what that means is when we're reading these graphs, the areas, or the work is going to be the area of the graph from between the points that it was required. It's asking. Sorry. So if we were to want to know the work from B to C, what we would need to find is the area from B to C. And to find that, it's just going to be the height times the length. In this case, the height is 2, and the length is 2, which will give us 4. Pretty easy. So we'll go back to our problem. So from B to C. Oops. It's going to be 4 joules, because that's just the area. Next one's asking us from A to B. I'm going to use a different color for this. To find the area from A to B, well, I told you it's just going to be, or the work from A to B, I told you it's just going to be the area during that interval, right? Take a look at that. That looks like a triangle. So the area for AB is going to be equal to a triangle, which is 1/2 base times height. And in this case, the base is going to be equal to the base is going to be equal to 2, and the height is going to be, or I'm sorry, 1, and the height is going to be equal to 2. 1/2 times 2 is 1 times 1. It's just going to give us 1. So when we do that, from A to B, it's going to be 1 joule. And it's asking us from A to D. Now, to solve the problem for A to D, what you should recognize is that if we know A through B, which we do, because that's just 1 joule, and we know B to C, which is pretty easy because we've already got that, that's 4 joules. And if we know C through D, if we were to combine all of those, we would find the total area, which would give us the total work during the whole interval. So what we're going to do is we are going to take our graph, take colors. We would need to find this area right here, and it's in our triangle. CD, 1/2. The base is going to be 1, 2, 3. And the height is going to be equal to 2. The area of CD is equal to 1/2 times 1 is 1 times 3 is going to give us 3. So that's going to be 3 joules. Combining together, that's going to give us A to D is going to give us 8 joules. There's our answer. Excellent. Now, the last thing I want to talk to you about today is the idea of power. And I'm going to pose a quick question for you. We're going to go back to the refrigerator. Suppose two men or two people are pushing similar fridges across the room the same distance. One person is much more powerful. Let's see this. What would be different? They're both pushing a refrigerator. Same refrigerator, same distance. What will be different if one is much more powerful? Jim? Excellent, good job. Yes. What we should recognize is that the refrigerator would be pushed much faster than with the person who's more powerful than the person who's not more powerful. What would that look like? What can we think of when we think of the equation? Well, we can say power is equal to work over time. It's a rate. Remember, this is the rate at which work is being done. That is the basic idea of power. So if we were to take a look at our last problem, it says a student needs money and has agreed to mow a lawn for some quick cash. Calculate the power produced by the student when he accelerates the mower with a force of 10 newtons through a distance of 4 meters in 3 seconds. We know that power is equal to work divided by time. And we know that work is equal to force times displacement divided by time. Power is equal to the force is 10 times 4 divided by 3. Power is equal to 40 divided by 3. And if we put this into our calculator, what we'll get is about 13.3. 13.3 joules. 10.0 newtons, 4.0, 3.0, the lowest significant figure is 2. So we can say the power is equal to 13 joules. Now, one thing I would do different when I'm working with the students is I typically like to, I use the method of I do, you do, we do. I like to have the students work a problem and then come together and work a larger problem together. Additionally, I will do checks for understanding, make sure the students are understanding the materials as we're going along. And I usually finish it up with a large check for understanding. A lot of times I would use an exit ticket. Thank you so much for giving me an opportunity to apply. If you have any questions, please let me know. Thank you.